Okay, good morning, Professor David J. De Los Reyes. Okay, it's October 5th, 16, 2023. The time is 6:33 a.m. Los Angeles time. Okay, my topic for this session will be a continuation of the long video format discussion on AC machines, and we are now on lesson number 41. Okay, we are running smooth. Okay, let's proceed. The title of the topic for this morning will be Alternating Current Machines, lesson number one. So, for those of you who are taking up electrical engineering or intend to take up electrical engineering, this is for you guys. AC machines, lesson number 41. The title of the topic will be True Power Loads and Open Delta Connection. We are given an open delta connection. We discussed already the closed delta and the Y connection. So one of the other variations of connection under three-phase transformers is if what happens if one of the transformers are actually damaged. So actually we could still operate the two transformers, but the orientation should be an open delta. The third one is missing. Okay, it is for repair, but we could still use these two here by using the so-called open delta connection, supplying a three-phase load, right? So there's a little bit what they call this discrepancy on the power delivered because the other one is missing. So the important thing that we will be discussing for this morning will be how will the two windings, okay, carry the loads at different power factor of the so-called balanced three-phase load. Uh, what will be the load of this one here and this number two here if the power factor is something like this? So I will be presenting three conditions in which we will try to analyze how the two windings, okay, will carry loads accordingly. Okay, let's proceed with the think of this concept of the discussion for this morning. We will try to bring out a vector diagram, so in the analysis of the question, we could base it here. Just to simplify the vector diagram, this will be the 90 into 70 degree line. This is the 0 and 180. The voltage per winding is this one. The voltage per winding is the voltage across this and this. I place it at the location 30 degrees. Okay, so it matches our equation. So this is at 30 degrees. Considering line current number one, the location should be at negative theta. It is below the 0 degree line, so this is IL1. Okay. And for IL2, the current delivered by winding number 2, okay, it is in this location here, and this is IL2. And I designate that the angle of difference between this voltage per phase and line current number 2 is plus angle theta, plus. Measured counterclockwise, this is measured clockwise, right? So this is the voltage per phase, okay? This is the current line number 1. This is line current number 2. Okay. Why am I presenting this vector diagram? I am presenting this vector diagram because in the computation of the power factor, it is by definition, the cosine of the angle between the voltage and the angle of the current. This is one definition of the power factor. It is the cosine of the angle between the angle of the voltage minus the angle of the current. Or meaning, this one here is the angle between the voltage and current. That is one of the definition of power factor under the study of AC circuits. Okay, so we will be using this concept here to compute our power factor. That's why I brought out or I bring out the vector diagram of the voltages and currents, okay? So we could show the angle between them, okay? By presenting the angle between them, okay, it will match our computation, okay? Okay, let's try to bring out the representation. Oh, this is angle theta. Am I still on camera? Oh, this is angle theta. I let angle theta equal to the power factor of the balanced three-phase load. On the secondary side, the three-phase load is balanced, and I represent it here. Angle theta will be the power factor of the balanced three-phase load. Okay. For the first winding, okay, the power factor will be cosine of 30 degrees minus theta, and for the second winding, first winding, second winding, power factor will be the cosine of the quantity 30 degrees plus theta. I got this one here, this one, 30 degrees minus theta. The angle between the phase voltage and line current number 1, it is this. So 30 degrees minus theta. That's why I brought out this one. So this one here matches with this, right? And the other one, power factor number 2, this should be number 1. Okay, let's now try to place this on screen. Number 1, number 2. Right? Power factor number 2 will be the cosine of the angle between, what do you call this, 30 degrees plus theta. Power factor number 2 will be 30 degrees plus theta. It is this. Right? So I place it here. 30 degrees minus theta is the angle between the first voltage in IL1, and 30 degrees plus theta. 30 degrees plus theta. It is this. I think this should be the second voltage. This should be number 1. Sorry for this one. This should be the voltage per phase number 2. So this is number 2. For this to be correct. Okay? 30 degrees plus theta is the angle between phase voltage number 2 and line current number 2. Okay? And for cosine of 30 degrees minus theta, 30 degrees minus theta, it is a voltage phase number 1 with respect to IL1. This is 30 degrees minus theta. For the equations to be correct. Okay? Okay, let's try to bring out the annotations now. And how the true windings will operate, okay? Will operate, meaning how much of the load will they carry at a certain power factor. When the power factor angle is actually 0 degree. 0 degree meaning the load is a pure lighting. Pure lighting, right? Angle is the power factor of the load is balanced three-phase load. When theta is 0, it's a pure lighting, all lights, right? Therefore, power factor number 1 should be equal to power factor number 2, and this should be equal to 1. How is that so? Power factor number 1 is actually cosine of 30 degrees minus theta, right? So when theta is 0, okay, when theta is 0, this will be 0. This will be 0. Okay? (30 degrees minus theta). Power factor number 1, power number 2. Okay, so minus theta. That's another thing. Minus theta, this is plus theta. Okay. When theta is 0, it's a pure lighting, right? Power factor number 1 should be equal to power factor number 2. Okay? And they will carry the same load. Oh, I think it's not 1. It should be cosine of 30 degrees. What's cosine of 30 degrees? What's cosine of 30 degrees? 0.866, right? I'm just checking. 30 degrees cosine. Oh, it's 0.866. Oh, sorry for this one. This should be 0.866. Okay, it's 0.866. Because when theta is 0, this will become 30 minus 0 is 30 degrees. 30 plus 0, 30 degrees plus 0 is still 30 degrees. So for power factor number 1 and number 2, it will be 0.866. Okay? And the condition will be since the power factor are the same, they will carry the same load. Okay? Okay? They will carry the same load. When the power factor is 0, it's a pure lighting. Power factor number 1 will be equal to power factor number 2, and this should be equal to 0.866. Okay? And when this occurs, they will carry the same load. Meaning the load carried by this winding here is same as the load carried by this one when the load is a pure lighting load. Okay. Number 2, when theta is 30 degrees, meaning the power factor is 30 degrees, right? So this will become minus 30 degrees. This is plus 30 degrees. So 30 minus 30, what will come out? It is 0, right? And what's the cosine of 0? It is 1. So when theta is 30 degrees, okay, the power factor of number 1 winding will be 1. And when theta is 30 degrees, 30 plus 30 will be 60. The cosine of 60 degrees is 0.5. So power factor number 2 will be 0.5. Okay. Number 1 is 1. Number 2 is 0.5. So when this occurs, winding number 1 will carry more load. Okay, because what they call this power is actually what they call this when this is greater, the true power will be greater, right? So when theta is 30 degrees, winding number 1 will carry more load because the power factor is 1. This is just 0.5. Okay. Third condition. Oh, this is just an illustrative example, so at least we could determine what will be the what they call this. Reaction of the windings and how they will carry load. When theta is 30 degrees, okay, this will become, 60 degrees, 60 degrees, this is 60 degrees, and this is 60 degrees. Okay, let's try to compute for power factor number 1. 30 minus 60 will be minus 30, right? Minus 30. And the cosine of minus 30 is still a positive thing, it is 0.866. So when theta is 60 degrees, when the power factor of the load is 60 degrees, power factor number 1 will be 0.866. Okay? The cosine of a negative angle is still plus, it is 0.866. Okay? And when this occurs, it will carry the entire load. How come it will carry the entire load? Okay, let's try to compute for the power factor number 2, the winding number 2. It should be 30 plus 60. 30 plus 60 is 90. Okay, and if we try to take the cosine of 90 is actually 0. So when theta is 60 degrees, power factor number 2 will be 0. Okay, so winding number 2 will not deliver no power. So I place it here since power factor winding number 2 will carry no power. Transformer number 1 will carry the entire load. Okay, will carry the entire load. So this is actually the worst case scenario because when winding number 1 will carry the entire load, okay, its power might not be more than enough to carry the given load. So, okay, it might be overloaded. So this is actually the worst condition that will occur for a open delta connection. Okay, let's try to bring out the true power for each winding. P1 is actually kVA per phase times the cosine of 30 degrees minus theta. This is power factor. Okay. And true power number 2 will be kVA per phase times cosine of 30 degrees plus theta. This is kVA, so this should be kilowatts. kVA, so this should be kilowatts. And the computation for the kVA per phase will be the product of voltage and current over 1,000. This is in kVA. Right? So what is needed here is computed here. You put it here, you put it here, times the power factor, because power factor is actually true power over apparent power. So true power will be equal to S times power factor. Okay? And what is S? S is actually kVA. So this is kVA times power factor is actually true power. True power. Okay? Okay, that's it guys. That's the way how an open delta transformer, what you call this, react for a three conditions, that is when theta is 0, theta is 30 degrees, and theta is 60 degrees. So engineers might be anticipating that is when the power factor of the load is 60 degrees, that is actually the worst case scenario that will come out. Because it might happen that the winding that will carry the entire load might be overloaded. Okay, good morning from Los Angeles. This is Professor David J. De Los Reyes.